Hi, this is Professor Gutierrez, and today we're going to look at Chapter 4, Section 2, Addition, Rule, and Multiplication. How do you add probabilities? How do you multiply them? How do you subtract, divide, conditional statements? Let's wait on those. We're going to look at addition, and we're going to look at multiplication. So let's go. All right, addition rule is basically when we have the probability of A or B. So what is the probability that either event A occurs, or that event B occurs, or that they both occur? This is called an inclusive OR. Right, so it could include both. Doesn't have to, but it could. There's also something called an exclusive OR, which we won't talk about, but that is if you get one or the other, but not both. Like if you want cake or ice cream for dessert, but you can't get both of them. That makes sense. That should make sense. I think that makes sense. All right, so that is the word OR, probability of A or B, and that is addition. So we're also going to talk about the word AND in the multiplication rule associated with it. All right, compound event is an event containing two or more simple events. So if we have two rolls of a die, two dice rolled, that could work. Probability of A or B is equal to P in a single trial. Event A occurs, or event B occurs, or they both occur. Fair enough. To find the probability of A or B, you add the number of ways A can occur and the number of ways that B can occur, but add in such a way that every outcome is counted only once. P of A or B is equal to the sum divided by the total number of outcomes in the sample space. Total number of outcomes in the sample space. I think that statement is a little bit off. But if you count the number of events in A or B and then divide by the total number, and each event is equally likely, then yes, that statement would be correct. Formal rule: probability of A or B is equal to probability of A plus probability of B minus probability of A and B. Haha, see? Perfect. That makes sense. Maybe? Yes? No? Maybe so? All right, so go ahead and write that down. And I'm going to write it down too. I'm going to write it down so you have time to write it down. And if you need a little extra time to write it down, you can pause the video, start it up again. Beautiful, beautiful thing. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So what we're going to look at is a Venn diagram. And I got one of them on another site here. All right, so we'll go here. Now, the sample space is the total of the 45 students. And the sample space is everything that is within this box. Okay? We have two events. We have students taking biology, which is 22 students taking biology. So the probability of someone taking biology is 22 over 45. And then we have the event of chemistry. Now, chemistry, 17 students are taking chemistry. So 17 over 45 would be the probability of that. And we have 15 students who are taking neither chemistry nor biology of these 45 students. Now, if I were to say the probability of A or B, I could have whether 8 students taking only chemistry, 13 taking only biology, and 9 taking both. So that would be 8 plus 9 plus 13, which is equal to, well, let's see, that's 3. One of those 3's can go with a 9. 2 can go with a 10, so that makes it 10 plus 10 plus 10. That is 30 over 45. And that will reduce to 2/3, or 0.667. P equals 0.667. But let's just say P of A or B is equal to 2/3. Now, let's look at the equation we wrote down. P of A or B is equal to, so that's back over here. Let me try this. Let's see how this works. That does not work. There we go. Ah! Well, that did not work the way I wanted to do. All right. That's fine. I don't need these rules. I can do this on my own. Okay, so we have this over here. I'm going to shrink it down a little bit. By the way, the page I got this from is really cool. So go ahead and take a look at it. Levelmathinstructor.com, and I'll show it up a little bit later. Let me shrink it up a bit so we can take a look. All right. So there is that. Now let me get a Word document out because I do like Word documents. I can do Word. I can do Word. That's what I do. And I can open a soda and you can hear it. I also keep having to record this, pause this recording, because everyone under the sun apparently wants to call me at once. Alright, so, document! So, the equation that we wrote down is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. There we go. Now, let's take a look at that. And let's plug the numbers in because we got those numbers. Probability of A or B equals, and we already calculated it just adding up 8, 9, and 13, but let's use the formula. That's equal to, well, there are 45 students, so 17 chemistry is 17 divided by 45. Plus, probability of B is 22 students, so 22 over 45. And then subtract 9 over 45. And that equals, well, we got 22 plus 17 minus 9. That gives us 30 over 45, which reduces to 2/3. So it gives us the same answer. And you can kind of see why when you look at the Venn diagram. We have these 17 students. If I count all 17, I'm counting the 8 and the 9. I add biology. When I do that, I count the 13 here and the 9 again. Therefore, I have to subtract this 9. And these 9 are both. Now, the probability of A and B, that both of them are correct, is 9 out of 45. And that's how we get that one. So that's how we get it from a Venn diagram. So these Venn diagrams can be pretty useful, and they can help to clarify a lot of the ways that, a lot of the numbers that you get. You can also just draw dots in Venn diagrams too. That can work as well. And you'll see that a little bit later. So let's go ahead and go back here. All right. So that's going to give you basically the formal addition rule, which can be pretty useful if you know PA, PB, and PB. Now, there are also some events that are called disjoint events or mutually exclusive events. In other words, they cannot occur at the same time. They do not overlap. So, what are examples of mutually exclusive events? Well, when we're talking about the boy or girl and we're looking at just that as a dichotomy, then we have boy or girl. You can't boy and girl. You're not going to have that event happen. So the probability of a disjoint event, A and B, if they're mutually exclusive, that means if one happens, the other can't, is 0. So probability of A and B is 0 if they're mutually exclusive. If they're mutually exclusive, therefore, if we go back up here, the probability A or B is simply equal to the probability of A plus the probability of B. All right, disjoint events. Male and female, they do not have a great bunch of mutually exclusive events here. An example of mutually exclusive event is a number is a number. See, I'm trying to come up with an event. I'm trying to come up with an example that is both mutually exclusive and okay, 3 and 5. You roll a die, it can't be both 3 and 5 at the same time. They're mutually exclusive events. Not disjoint. Randomly selecting someone from taking a statistics course. For example, I choose you, whoever you are, if you're listening. If you're not listening, I choose you too. Randomly selecting someone who is female. All right, select a person can be both. So someone could be female and in the stats course, or someone could be just female, or someone could just be in the stats course. And if I randomly selected among the pool of all people taking statistics and all women, my suspicion is that the probability would be higher that it is female, because we have 3.5 billion women, and we probably have fewer than 1 million taking statistics, I'm assuming, at the moment. And probably fewer than that in this class. So, yeah, okay. So that is going to be the word or, right? Probability of A or B. We want to know what that means. It's going to be addition. We add them and then subtract any overlap. All right, complementary events. So this is one of the things I said I didn't want to do. Because if you have complementary events, if you add the probability of 2 complementary events, your probability is going to be 1. The probability of something happening and it not happening is 1. The probability of someone being male or female is 1. The probability of Schrodinger's cat being alive or dead is, I don't know. You have to figure out the quantum mechanics for that one. If you know quantum mechanics, you get the joke. Could that cat be both alive and dead at the same time? Yes. See? Quantum mechanics jokes. They are loads of laughs. But that makes sense. You either are or you're not. You're with us or you're against us. And that's 1. Everyone's that way. Probability of A plus probability of A bar is equal to 1. Probability of A bar is equal to 1 minus probability of A. Or probability of A is equal to 1 minus probability of A bar. Ooh. Now, that is a very useful equation. So I suggest you write this one up. P of A is equal to 1 minus P of A bar. Because this is something that we would use a lot. And I'll give you a quick example. Let's say that there's a family that has, they have 4 kids, and all the kids are boys. Randomly selecting, what would the odds have been that at least, if someone has 4 kids, that all 4 of them, that none of them would be girls? In other words, that you have at least 1 girl. So the probability of having at least 1 girl is equal to the probability, figure out what a probability for 1 girl, probability for 2 girls, probability for 3, probability for 4. You add all of those up, and then you get the probability for at least 1 girl. However, okay, and let's go to Excel. There we go. So let's say 4 kids, and what is probability of girl being greater than 0? That's equal to probability that the number of girls equals 1, plus the probability that the girls equal 2, capital P, plus the probability that the girl equals 3, plus the probability that the girl equals 4. Well, that stinks. That's a lot of probabilities to calculate, and they are not simple probabilities to calculate. Some of them can get very messy. We deal with factors, we deal with, we deal with factors a lot. Not factors. Factors? Vectors. No. Exclamation points. What are those called? I will pause because I really should know what they're called. Factorial. I got it. All right, that's what it was. All right, so anyway. So going back up to the document, taking a look here, probability, Well, that can be a lot of probabilities, but you can also say the probability of having a girl greater than 0 is equal to 1 minus the probability. What's the probability that you don't have greater than 0 girls? Well, that's that girl equals 0, which is equal to 1 minus 1/2 to the 4th power, which equals, let's see, 2, 4, 8, 16, 15 16ths. So rather than calculating 3 difficult calculations, you do 1 calculation. And the probability that G is greater than 0 is simply 1 minus probability of the girl equal to 0. Fantastic. Fantastic. I use that probably more than a lot of these other rules. So, know it. All right. Example, sleepwalking. Anybody sleepwalk here? Nope. No, I don't. I have had students who sleepwalk. Not in class. That would be weird. Well, I can say not that I know of in class anyway. All right. Based on a journal article. That's well referenced. The probability of randomly selecting someone who has sleptwalked, is 0.292. So probability that someone sleepwalked is 0.292 based on the data from prevalence and comorbidity of nocturnal wandering in U.S. general population by Ohian et al. Who's al? Doesn't matter. Neurology, volume 78, number 20. Okay, that is well referenced, so I take back my snarky remark from the beginning. Oh, by the way, et al. Just means and others. It's Latin. Fancy. Ooh. Person randomly selected from the probability that someone who has not sleptwalked. Well, that's simply 1 minus 0.292. Let's see if that's what they do. That is what they do. 0.708. So, 0.708. Now, I ask you, okay, so I took a little pause there. Probability that someone has sleptwalked is 0.292. So the probability that nobody has sleptwalked in the class is going to be, well, each person is 0.292. So that is going to be, or the probability that we have at least one sleepwalker in the class. Let me rephrase that. Yeah. What is the probability that we have 0 sleepwalkers in the class? Now, if someone is not a sleepwalker, the probability is going to be 0.708. So, that will be 0.708 to the 28th power. I don't know why there's a V there. And that is equal to, using my trusty little calculator here, to the 28th power. It's going to give me 0.000063. So, I'm going to guess we have some sleepwalkers in the class, or at least people who have sleptwalked. That doesn't mean you currently sleepwalk. That is interesting. All right. All right, multiplication rule. We like multiplying. Multiplying's fun. We can do it. Probability events A and B occur in a trial. So now we're doing this one a little bit differently. Probability of A and B is equal to the probability of event A occurs in the first trial and event B occurs in the second. All right. So this is talking about two different trials. And this one, probability of A given B, that's how you read that, probability of B given A represents the probability of B occurs after it is assumed that A has already occurred. If it's cloudy, what are the chances that it's raining? So the chances of it's raining are a certain amount, but if it's cloudy, the chances of raining are higher. So what are the chances of it raining if it's cloudy? What are the chances of it raining if it's not cloudy? There are no clouds in the sky. Can it rain? Maybe. I am not sure about that one. Intuitive multiplication, or intuition, always leading you down weird paths. To find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the event B, and be sure the probability of event B is found to assume that event A has already occurred. Huh? What? Okay, so what they're saying is, in a weird way, the probability of A and B is equal to the probability of A times the probability of B given A. So the chances of it being raining, and being cloudy are the chances of it raining and the chances of it being cloudy given that it's raining. Wait. Raining and cloudy. Raining, cloudy, raining. Okay. The probability that it's raining and cloudy is equal to the probability that it is raining times the probability that it's cloudy given that it's raining. There we go. And you can also just use that to flip it around. Probability of B given A is equal to the probability of A and B over the probability of A, which they show on the next slide. They don't show on the next slide. I'm going to show it. I'll type it out. I can do that. All right, so in addition to that rule that they just gave you, you can also have the probability of B given A is equal to the probability of A and B divided by the probability of A. There we go. Yep. And sometimes you want to know this conditional probability because you know A has already occurred. So then what's the probability that B occurs given that A has already occurred? And that's what you're looking at. And I have a loud chair, so I apologize for that. All right, independent. Two events, A and B, are independent if the occurrence of one does not affect the probability of the other. Several events are independent if it occurs. Any does not affect the probability of occurrence. A and B are not independent, they are dependent. And finding dependence is pretty cool if we can find it, but some things are independent. So if I roll one die and it calls up a 3, I roll a second die, that 3 is not going to affect the second roll. On the other hand, if I put clouds in the sky, chances are it is going to rain. That does affect the probability. All right. Example, drug screenings and basic multiplication rules. We're going to use the multiplication rule. We got 50 test results from subjects who use drugs and are shown below. 45 positive test results, 5 negative test results. The negatives are called false negatives. So you got false positives, you got false negatives. So a total of 50 drug users. If 2 of the subjects are randomly selected with replacement, it means you put them back in, then you randomly select. You can find the probability the first selected person will have a positive test result and the second person will have a negative test result. So these are independent. You're putting every person back, so that doesn't affect anything. So you simply take the number of people who have positive test results divided by 50, Then take the people who have the number of negative test results and divide it by 50. Now, selected without repeating. That one is a little bit more complicated. 45. 5 over 50. Multiply them. We're awesome. So the chance of that happening is 9. Now, what about if we do it without replacement? The second probability is 5 over 49. So that's pretty cool. Now the probability is a little... So why 5 over 49? There's still 5 negatives out of those 50. But there are only 49 people left. That's why. So the probability changes slightly. And the smaller our sample, the more that will cause it to change. So sampling. We can do sampling with replacement. Selections are independent, or sampling without replacement. Selections will be dependent. Now, this is kind of the same thing. Treating dependent events and independent events. 5% guideline. When sampling without replacement and the sample size is no more than 5% of the population size, treat the selections as being independent, even though they're actually dependent. And that's because you will have such a large 5% of the population. The reason being is that taking out that few people isn't going to make a huge difference. So just treat them as independent. All right, and this gives you an example of out of the people in the United States. And obviously, if you choose one person out of the United States, then you choose another person, even if you don't do replacement, it's not going to affect things that much. Assume 10% of American adults use drugs. So that means about 3 of you, including me, maybe. All right. So we can treat it as without replacement because it's such a large number. So 0.1 times 0.1 times 0.1 is going to be a 0.1% chance that all 3 selected adults use drugs. If it's random. Got to be random. All right, so redundancy. All right, the principle of redundancy is that we use it increases reliability because we have multiple components doing the same thing. And if one fails, the other won't fail. Or at least that's the idea. Not everything depends on a simple event. So example, Airbus. We don't like Airbus. We like Boeing here. Modern aircraft are highly reliable, and one design feature contributing to that reliability is the use of redundancy, where critical components are duplicated so that if one fails, the other will work. For example, Airbus 310 twin-engine airliner has 3 independent hydraulic systems. So if one system fails, a full flight control is maintained with another functioning system. So you got 3. 1 fails, 2 to back it up. 2 fails, 1 to back it up. 3 fail. Not so good. Maybe they should have got a 4th one. Who knows? All right, assume a typical flight, the probability of a hydraulic system failure is 0.002. So that's not too bad. Airbus would have 1 hydraulic system. The probability aircraft flight control would work is going to be 0.998. 1 minus 0.002. Given the Airbus has 3, what is the probability on a typical flight control can be maintained with a working hydraulic system? So 0.998. So we got 0.002. 0.002 times 0.002. So the probability is going to be 0.999999992. So in other words, you're probably pretty good. Oh, but this is sorry. Having 3 decreases not by a factor of 1/3, but by a factor of 1 over 250,000. So not bad. You need hydraulics after all. Are they that important? Summary of the addition rule. Addition is for or, multiplication is for and. All right. And that is it for section 2. I will see you soon. That's under 30 minutes too. Woohoo! Of course, now it's like 3 seconds, so I might not make it.